Okay. Good evening, everyone. Today I'll be taking the solve with a session, and we'll start in just a few more minutes. We'll wait for a few more people to join, and then we'll start.
So please do share the PDF of the solve with us on the calendar also after the class is over.
Right, sure.
Thank you.
Sir, yesterday's session still asking for request permission.
Sorry.
Yesterday's session, recorded session, YouTube
Oh, the
session.
TS session. Yes, I will
Yes,
add that. I will add that. Sorry, I will add that.
yeah. It is asking for access.
Correct. Yeah, I'll add that by today.
Yeah, thank you, sir.
Okay, let's start. Okay, so we'll be discussing some specific questions from perceptron and logistic regression today. Okay, so the first question is yeah, okay. So some of you may be wondering why I'm taking the session. I mean, today I'm taking the solve with instructor session. Okay, so yeah,
So how many questions are
we have. I don't know the exact number of questions actually. Some of the questions don't have a number, so I'm not sure of the exact number of questions. Okay, we'll see it as it goes. Okay, we'll start. So we know that. So the first question is: we know that the decision boundary learned by perceptron is a line in R2, right? So if you have some data points, you have some decision boundary like this, right? Where the positive points are here, the negative points are here. So the question is: we also observe that it divides the entire space of R2 into two regions, right? So that is this region and this region. Suppose that input vector is actually in R5, then the perceptron decision boundary will divide the whole R5 space into how many regions? Okay. So for this question, one simple thing that you need to remember is that ultimately perceptron is a binary classification algorithm, correct? So ultimately, no matter how much, I mean, whether the input data is in R5 or R6 or any RD, that doesn't matter. Ultimately, we want to divide the space into two regions, right? One in the positive class, one space which contains all the points in the positive class, and one space which contains all the points in the negative class. Okay, so irrespective of which dimension we are in, 2 is the correct answer. Such that the W transpose X, if it's greater than or equal to 0, it will belong to the +1 class. If it's less than 0, it will belong to the -1 class, where W can belong to any dimension.
Can I just show the question once again?
Yeah, sure.
Okay.
All right. Now, second question is, so consider this following table where x1 and x2 are features packed into a single vector, x is equal to x1, x2, and y is a label. Y is the label. Okay. Suppose that perceptron is used to classify the data points, and suppose further that the weight w are initialized to 1, comma 1. The following rule is used for classification. So they've given the rule, and perceptron learning algorithm is used to update the weight vector in a weight vector w. Then how many times the weight vector w will get updated during the entire training process? Okay, cycle through the data points in the given order. Right, so either we have to conclude that perceptron does not converge at all. So if we get a particular w which is equal to one of the earlier w's, then we'll conclude that perceptron has not converged at all. On the other hand, if we we get a particular w which perfectly classifies all the points into the +1 class or the -1 class, then we will conclude that perceptron has converged. Okay, so for this, one special thing about this question is, we initialize the vector to be we initialize the weight vector to be 1, comma 1. Usually by convention, if nothing is mentioned, we take 0, comma 0. Here we've taken 1, comma 1. And another unique thing about this particular question is that normally the rule we follow is this: if w transpose x is greater than or equal to 0, then we'll call it +1 class, otherwise we'll call it the -1 class. Whereas here they said if it's greater than 0 is the +1 class, if it is less than or equal to 0, then it's the -1 class. So this equality condition has been flipped. Okay, so now, did someone raise their hand or something? I guess not. Okay, so
So, sir, we are looking for a W that gives the zero error, right?
yeah, which correctly classifies all the points or 0 error. Correct. Okay. So they've given that it is 1, comma 1, right? So the weight vector is 1, comma 1. So let us proceed in the same order. Let us see. So we have for the first point x1, right? So we have w transpose x1 is equal to 1, comma 1 transpose with 0, comma 0, right? So that is just going to give me 0. That's just going to give me 0, right? And 0 falls in this case, which means, so I will call this y hat, predicted y, and this is the true y. Okay, so the true y is obviously -1, that's given here. The predicted y is because it falls in this condition, we'll take that also to be -1. Okay, what about the second one? W transpose x2 is equal to 1, 1 dotted with 0, 1, and that is 1. Okay, which is greater than 0, so it is +1 class. Here also it's +1 class. Now W transpose x3 is equal to 1, 1 dotted with 1, 0. Similarly, this is also 1, this is +1 class, this is +1 class. Finally, we have W transpose x4, which is 1, 1 dotted with 1, 1, which is 2, right? So yeah, which is 2, which is again +1, and this class is also +1, which means actually everything is matching, right? In the first iteration itself, it has converged. Our initial weight vector w0 has turned out to be a weight vector which correctly classifies all the points. So which means that, what's the question that's asked actually? How many times the weight vector will get updated during the process? So it will not get updated at all. The first vector itself correctly classified everything. So it will not update 0 times. Okay. Next question is, so which of the following options are correct with respect to perceptron and logistic regression? Okay, so the first statement says perceptron is robust to outliers because it only updates weights for misclassified points. That is the opposite of robust, right? So when if there is a single misclassified data point, then perceptron will heavily change the weight vector in order to correct that particular data point. So if anything, it is the opposite of robust. Just for one data point, it will change the entire weight vector, even if it is classifying all the other data points correctly. So this is definitely an incorrect statement. Okay. Now, A logistic regression assumes that the data is perfectly linearly separable for effective training. Is this true? Again, it's false, right? Because in logistic regression, we assign probabilities that the class is +1 or the class is -1. So, which means logistic regression doesn't assume linear separability. We can model even non-linearly separable, I mean, even data sets which are not linearly separable. Okay? And for a linearly separable data set, the perceptron algorithm always makes R square by gamma square mistakes. Okay, so this is also incorrect because the upper bound is R square by gamma square. Doesn't mean that every time it will make that many number of mistakes. Depending on how you cycle through the data points, perceptron may return a different weight vector. That is true. So one thing about perceptron that you need to keep in mind is it may not give you, so it is only trying to find a feasible W. So I actually discussed this yesterday also in the TA session, but in case you are not there, so what is perceptron doing is, so let us say that there are some data points like this. Okay, these are the positive data points, and here these are the negative data points. So it is not that there is only one W. Of course, if you look at it, it seems like this should be the best possible W, right? That separates these data points, in which case this will be the decision boundary. But this is not the only possible W. In fact, this x-axis itself, W can be along the x-axis itself, right? In which case this y-axis will be the decision boundary, and every point that is on the right side of the y-axis is a positive point. Every point on the this side of the on this side of the y-axis is a negative point, right? But clearly this and this are not the same, right? So one of these W's might be better than the other, but perceptron is, for perceptron's point of view, it doesn't really matter. It just wants to identify one W which correctly classifies all the points. As long as it correctly classifies it, then perceptron is not bothered about whether there is a better W or if this is the best W or any such thing. Okay, so depending on how you initialize perceptron and depending on the order in which you cycle through the data points and all that, you could arrive at a different W also. That's perfectly reasonable. Okay, so that's a correct statement. So the next one is, in perceptron, as the margin decreases, the number of updates increases. That also seems to be valid, because if the margin is much closer, then that means there are not as many feasible W's, right? The more the margin, there are more the number of feasible W's. Whereas even in this itself, in this data set itself, if the data points were closer to this margin, then and even to the extent of so if the data points were like this, right, then the purple line, which means this one, is no longer a feasible W, right? So perceptron cannot converge after these many number of iterations. It will have to keep searching until eventually it finds this particular W. So that seems to make sense. We'll take that for now, but we'll check that. We'll check whether that's true or false. Okay. Then actually let's check that now itself. Yeah, okay. Also, you can prove it mathematically, because we know that for a linearly separable data set, the mistakes it makes is less than or equal to R square by gamma square, right? So if gamma square decreases, then the number of mistakes this is the number of mistakes, right? So the number of mistakes will increase. So that is, the upper bound itself increases. So, and since the number of mistakes is the same as the number of iterations, it means that the number of updates also increases. Okay, so that is a mathematical way to understand the same thing. Logistic regression uses cross entropy loss. No, it uses well, I mean, we could, I guess. I think we just use sigmoid, right? We just use the sigmoid function.
No,
Okay, yeah, correct. We can use cross entropy loss also. Yeah, sorry about that. Logistic regression. Okay, the loss that we came up with, the objective function that we were trying to define for logistic regression, it does use cross entropy loss. Okay, cross entropy loss is basically that minus p. Okay, sorry, not minus p. I think it is minus y times log of p plus 1 minus y times log of 1 minus p, right?
Minus 1 minus 0. Okay, it has to be in bracket. Okay,
Yeah,
okay.
in brackets, yes. Correct. Okay, so this is a loss that logistic regression actually uses, and this is also called the log loss because you have these log, right? So actually, for any one of the terms, either it will be y or 1 minus y. So one of the terms will not be there, the other term will only be there. Okay, and so what we are trying to do is we are trying to minimize the difference between the predicted probability and the true label, that is y is equal to 1 or y is equal to 0, and this is the loss that we are trying to minimize. Okay, so this is also a correct statement. Then perceptron guarantees that the learned weights will be optimal for linearly separable data. We cannot say that it will be optimal, right? So it will work, but it's not optimal. Optimum means we are trying to optimize some function. Here there is no objective function only for perceptron that we are trying to optimize. So we cannot say that it will be optimal, and certainly we cannot guarantee it. So this is an incorrect statement.
Also, there is only an upper bound on the number of mistakes, right? So that's why also we can't say that.
Yeah. In a sense, there's not a lower bound. Is that what you're saying?
Sorry, what?
Do you mean to say that there is not a lower bound? Is that what you're saying?
No, because the mistake, the number of mistakes are given as by less than equal to r square by gamma square, right?
Right.
So basically, so there is no optimal number basically.
Yeah, correct. There is no optimal number. So, I mean, if we have an objective function, then we can maximize or minimize that function to get to reach some sort of optimum. But here, we can't do that. Okay, and I mean, and like I said, if there are two W's and one of them is clearly preferred over the other, but for perceptron's point of view, that doesn't matter. So it will, as long as it correctly classifies all the training data points, it will stop there. Okay, and then the gradient of the logistic regression loss with respect to the weights W is proportional to the difference between the predicted probabilities and the actual labels. Gradient of the logistic regression loss with respect to the weights W is proportional to the difference between the predicted probabilities and the actual labels. Yeah, I think it is a true statement because in your in the gradient function of logistic regression, so we in the lecture we saw that it is some linear combination of the data points, right? So some c1 x1 plus some c2 x2 plus so on until some cn xn, right? And where the c is actually nothing but yi minus I think it was 1 divided by 1 plus e power minus of w transpose xi. I think this was the weight for each of the labels. Okay, and this is of course sum over all I is equal to 1 to n. So which means that the weight vector, the gradient of the logistic regression, so this is the gradient, and this gradient is proportional to the difference between the predicted probabilities and the actual labels. I think that's a true statement. Yes, it is a true statement. Okay, so yeah, so this is yi, and then this 1 divided by 1 plus e power minus of w transpose xi, right? So this can also be written as y hat of I, right? Because this is your predicted probability for the true y. Okay, so this is also a correct statement. Now for logistic regression, as w transpose x tends to infinity, the predicted probability tends to 0. That is also false because the predicted probability is basically this, right? 1 by 1 plus e power minus of w transpose x. So if you replace this with infinity, of course, you have to do this under a limit. Otherwise, you can't simply replace it with infinity. But assuming you replace it under some limit, okay. So this would be 1 divided by 1 plus e power 1 by infinity, and 1 by infinity is just 0, right? So this is 1 divided by 1, which is just 1. So as w transpose x converges to infinity, as w transpose x diverges to infinity, the predicted probability will tend to 1. So this is also an incorrect statement. Okay. Okay. So now consider a logistic regression model that is trained on videos to detect objectionable content. Videos with objectionable content belong to the positive class. So this is label 1. Harmless videos belong to the negative class, label 0. A good detector should be able to correctly identify almost all videos that are objectionable. Okay. So this is a key point. This is also something related to what I was discussing yesterday, right, in the TA session. So if you attended, basically the example was that if we are trying to give a loan to somebody, okay, so let's say you're a banker and you're trying to decide which person to give a loan to, okay. So if you used logistic regression for this, so it is not just a classification algorithm, right, which means it is not just returning me whether to, that is yes or no, should I give a loan to that person or not. It's not just returning that, it is also returning to me whether, I mean, what is the probability with which I should give the person the loan, right? Which is, I mean, which is like a way of saying what is the probability that the person will default, or what is the probability that the person will repay the loan, right? So, of course, you can set the threshold at 0.5, right? And that will give you the most accurate prediction for whether the person will default or whether the person will not default. But maximizing this number, that is maximizing the prediction accuracy, is not the same as actually deciding whether to lend or not. Okay, because I might be a more conservative investor, right? So I am okay with not giving a loan to some people who might not default, right? If their credit score and all that is bad, so I might be comfortable earning some lesser amount of money. So like I don't want to take any risk. I want to minimize all the chances of default. So I'm okay with actually ignoring some people who might actually repay the loan. But one thing I want to ensure is that I definitely don't want to lend to someone who will default, right? That is something that I want to avoid at all cost. And in that case, it is okay if I actually don't lend to some people who may actually be genuine and who may actually repay the money also. So similarly, this is also a similar question. So I am okay with okay, so basically it's saying if it incorrectly classifies even a single video that has some inappropriate content in it, that could have some serious consequences, as millions of people might end up watching the video. In this process, the detector may classify some harmless video as belonging to the positive class. Okay, but that is a price we are willing to pay, right? So if you go on to later weeks of MLT and then eventually in MLP as well, you will learn about metrics called precision and recall. Okay. In simple words, precision means out of what I predict to be, uh, out of my predictions, I want my predictions to be accurate. Okay. If I predict some video as containing inappropriate content, then I want that prediction to be accurate. Recall means I am trying to optimize for if I mean all the videos that have inappropriate content should be flagged by this particular detector. In that process, it is okay if I accidentally flag some videos which are actually harmless, but still it is flagged by this model as having inappropriate content. That is okay. So in this question, we want to optimize for recall. Okay. So, and in that process, if our precision goes down, that is fine. If I accidentally, flag some videos as belonging to the positive class, even though they actually belong to the negative class, that's fine. Okay. So, which means we have to pick the threshold at a low value, which means, let's say, for example, the probability that the video has objectionable content is 20%, or yeah, fine, let's say 20%. Okay. If it is 20% itself, I will flag it as belonging to the positive one, the +1 class. Okay. Which means if it is, I mean, if even if there is only a 20% probability, normally you would only if it is greater than 50%, you would flag it as belonging to the positive class, right? But here, even if it is 20% or some other threshold like this, I will say that it belongs to the positive class. Okay, because I want to minimize the actual objectionable videos from being released to the public, right? So which means that this threshold should be set at a low value. Okay, and this does increase harmless videos being flagged as objectionable, but it is acceptable for us. Okay, so the next question is, if we use gradient ascent to find x comma y such that f of x comma y is equal to 3 plus x plus y minus x square minus y square is maximum. Okay, then after how many iterations will the algorithm stop? Okay, so use 2 comma 2 as initialization point and 0.5 as learning rate. Okay, so here we have okay, so one thing here is we are using gradient ascent. Okay, normally we are used to gradient descent, but here we are using gradient ascent.
Plus theta, right?
Yeah, exactly. Plus eta times the del f of w. Okay, so and second thing is the question is not asking after how many iterations the algorithm will converge. The question is asking after how many iterations the algorithm will stop. Okay, so if we have reached the lowest possible value, then at that point we say, at least for the purpose of our course, we say that the convention that we follow is if we have reached the lowest possible value of the objective function, we say that the algorithm has converged. But the problem is, with that iteration alone, we cannot tell whether that is the lowest possible point or not. So even though it has technically converged, we won't be able to identify whether it has converged or not without running the algorithm for one more iteration. Okay, and that one more algorithm which we have to run, after that the algorithm will stop. So that extra iteration that we are running for is called a termination condition. Okay, and so whatever algorithm, I mean whatever number of steps it converges in, it takes one more iteration for it to terminate. Okay, we saw something similar for k-means as well, and that is the same principle that we will follow here. The only difference is they have actually asked for stop, which means termination condition. So we have to include one the extra iteration, which is which is what proves to us that the algorithm has converged. Okay, so with all that said, let's take this f of x comma y, and we need to take the derivative of this. So actually we need to find del of f of x comma y, right? So, and 2 comma 2 as the initialization point and 0.5 as the learning rate. Okay, so del f of x comma y. So for this, let's just take derivative of f of x comma y with respect to x first, right? So that is, I mean, basically you treat everything else as constant. So which means, yeah, so we only have this term, x term and minus x square term. So this just becomes 1 minus 2x. Okay, and then similarly del of dou f of x comma y with respect to y will be the same thing, 1 minus 2y. And if I put this into a vector, right, so this vector is nothing but 1 minus 2x comma 1 minus 2y. Okay, so we have our original point as the initialization point. Okay, and so I mean the update rule will be, we have 2 comma 2 plus, this is gradient ascent, so plus and eta times, so 0.5 times 1 minus 2x and 1 minus 2y evaluated at 2 comma 2. So this will be 1 minus 2 times 2 comma 1 minus 2 times 2 again, right? So this is 2 comma 2 plus 0.5 into 1 minus 4 is minus 3 comma minus 3, right? And this is 2 comma 2 plus minus 1.5 comma minus 1.5, which is 0.5 comma 0.5. Okay, so we've run this algorithm for one iteration. Now let's run it for the second iteration also. We start at 0.5 comma 0.5 plus the learning rate is the same, it's a constant here. Okay, and then
0, 0.
0, 0 is it?
Yes.
Okay, yeah, it's 1 minus 2 times 0.5 and again 1 minus 2 times, okay, this is an into by the way, okay, 1 minus 2 times 0.5. So
Stop
this
there.
is, yeah, so this is 0 and this is also 0. Okay, so this is again 0.5 comma 0.5. So after 2 iterations, so it has actually, so only after completing this iteration we will know that it has converged. But it has converged here and it has terminated here. Okay, and what are they asking? They are asking for when will the algorithm stop? So which means they are asking for the termination condition, which means after 2 iterations, yeah, after 2 iterations the algorithm has terminated. So we should actually say terminated here, terminated after 2 iterations.
So even if it asks like when does it converge, do we have to do the second step iteration too?
Yeah, because
Will we
without doing the second step, you won't know that that is the lowest possible value. I mean, of course, technically, I agree with what you're saying that, if you compute this del f of w and this turns out to be 0, right?
Correct.
If this turns out to be 0, then
It
you
won't
need to complete this iteration actually. Here itself, you can find out that this point will be the convergence point. So in this case, if they ask it's converged, and if you check this and it turns out to be 0, 0, then you need not compute this, although it's just one step away, but you need not compute it technically speaking.
Okay.
Okay, so right. So for this data set, is the perceptron algorithm likely to take less number of? Okay, so for which data set is perceptron likely to take less number of iterations to converge?
Figure 2.
Correct.
Figure 2.
Yeah, that's correct because it has a larger margin, right? So it has a larger margin here, and naturally L is
Less number of
proportional to
mistakes.
R squared divided by gamma square, right? And if the bigger the gamma square, the smaller the L, right? So naturally, this will take more number of iterations, and this will take less number of iterations. All right. I didn't skip anything, right? Yeah. Okay.
Excuse me, sir.
Yes.
Sir, can you please explain that question again?
Oh, this one is it?
Yes.
Okay. So for this, the question is, for which of the following 2 data sets is perceptron likely to take less number of iterations to converge? Okay. And okay, see, one thing I'll tell you is that first I'll explain it geometrically. Okay. If I'm explaining it geometrically, it means that, see, for this particular data set, then what is the true value of W, or what is the most likely true value of W? The W points something like this, right? So assuming that red is the positive class and green is the negative class, otherwise it'll be the opposite. So if this is the W, then this will be the decision boundary, correct? Are you following until this point?
Yes, sir.
And see, if I come up with any other W, for example, if I come up with some W like this, okay, then the decision boundary will shift something like this, right? But that is not but then perceptron will not converge because there are some misclassifications here, there are some misclassifications here, right? So even if I come up with this W, which is actually very close to this one, right? It is very close, but it won't converge. It will have to keep running for more and more iterations, correct? Okay, but now look at this particular data set, the second one. Okay, so of course, here also this seems to be the best possible choice of W. I agree with that. And if ideally that is the best W that you want. But perceptron is not searching for best possible W, it is searching for any feasible W. So let me say that I come up with some W like this, okay, this W. And this W comes up with a decision boundary like this. Okay, here perceptron has converged, right? So even if I come up with some W like this, or even if I come up with some W that is like this, sorry, not that much extreme, but something like this, and some kind of boundary like this, here also perceptron will converge. So there are many different possible W's that I can come up with, right? And the algorithm will still converge, which means it is not going to search for so long. As long as it finds one of these W's, it will converge. Whereas for this algorithm, if I only if it finds this particular W, it will converge. So that is one intuitive way to understand this. Okay. Now, yes, Kiran.
So, sir, how do we know how many iterations we have to perform this algorithm?
I mean, if
Like-
this kind of data set is given, then if nothing is given about the number of points, you cannot find anything about the exact number of iterations. Only if you run perceptron, you can find exactly what number of iterations it will take to converge. Okay, but suppose you just want to find an upper bound for the number of iterations, then you can use that r square by gamma square, because that gives you an upper bound. Suppose r is given in the question and gamma is given in the question, then you can find an upper bound for the number of iterations that perceptron will take to converge.
Okay, so
in this question, of course, the gamma is very clearly much higher in this data set, right? So gamma is basically the distance to the closest point, right? So in this case, gamma seems to be much higher. So I mean, first of all, the simple way is to understand it like intuitively, like I told, right? The second way, if you want to prove it mathematically, is to say that in this question, the first case, the gamma here is almost 0, so it is very, 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 very small, right? So this must be the gamma, correct? So this width is plus gamma, and this width is and then this width is minus gamma. So some very, very tiny line. Okay, so gamma here is very small. So let us call this gamma 1. Okay, and then the number of mistakes that this perceptron will make, I'm calling that L1, will be less than or equal to r square divided by gamma 1 square. All right, and this is some number of mistakes. Whereas for this algorithm, the gamma here is much larger, right? And here it is L2 will be less than or equal to R2 square divided by gamma 2 square. Okay, so here this gamma is much, much, much larger than the first one, right? It is way larger, which means if this number is larger, then this number will be smaller. That is, L2 is inversely proportional to gamma 2, right? So which means that L2 will make, I mean, the L2 will be much lower than L1, because this, if you run perceptron here, it is likely to make far fewer mistakes. Okay. So,
so what do we do for checking like convergence? Should we check the error?
no, here they're not asking about convergence. I mean, they're just asking which algorithm will take less number of iterations.
Yeah, that's okay.
So you just need to answer purely based on gamma, just visual inspection, that's all. They don't expect you to do any calculation here.
Okay.
Okay, I think you may be confused because here they've given that it took 2,300 rounds and this took 264 rounds, but that is because
I did
they
not see
actually
that.
plotted this in some, I mean, either scikit-learn or maybe they coded it using NumPy something. But that is only given because they created the data set and then they ran perceptron in NumPy or scikit-learn or something. Okay. But if you actually just look at it, you cannot say anything about it, apart from the fact that this looks much wider and therefore it will take less number of iterations.
So even in NumPy, what do we do? Should we like check the error to be 0 or not every iteration?
Yes, you have to check that. So you will actually have to do every iteration of perceptron, and then at some point you will have an error is equal to 0. Of course, assuming it's linearly separable. In both these cases, it is linearly separable. So at some point, it will correctly classify for all the points, right? So you take every x1 comma y1 pair, and W transpose x1 will be equal to y1. I mean, sorry, the sign of W transpose x1 will be equal to y1 for all the data points. In which case, you can say that that is the number of iterations in which perceptron has converged. All right, so let's go to the next question.
Sir, one thing, just one question. Can you just go above?
Yeah, sure.
Yeah, in this one, sir, if we want to geometrically interpret, for example, regarding the radius assumption, okay, R. So how can you just show it, like how in this case?
Okay, so here the radius seems to be from between -2 to +2, and here the radius seems to be somewhere like minus 1.3 to. Sorry.
Got it. Understood, sir. Understood.
Yeah, so I mean, because of the scale that is given in the question, we can assume that.
Okay, the maximum data point and the minimum data point, right? Basically. We'll have to check that.
Yeah, the maximum data point in terms of distance from origin. Okay, the radius is based on distance from origin,
Correct.
whereas the minimum, that is gamma, is based on the W transpose X value of the closest data point.
Understood. Basically, say for example, the one which is lying on the boundary, right, for gamma.
Yeah. So, for example, yeah, exactly. So this point and this point, etc.
Understood.
The thing is, this point and this point have the same gamma value, and this point also has the same gamma value. You might think that this point is actually closer to the origin, right, than this point. But the thing is, they have the same W transpose X value. All of them lie on this line, right? So all of them, have the same distance from. Uh, all of them make the same dot product with the W vector. So that is your condition for gamma. Which of the data points make the least dot product with the W vector?
Least dot product for with the W vector, right?
Yes.
That is the gamma, right?
Correct.
Right. Because a point on the extreme end and a point in the middle would have a different dot product, right, sir?
No, if you take this particular point, okay, let us say that this point and this point lie on the same line, okay? So
Correct.
let me take this point and this point. Actually, this point is much more closer to the origin, right? But that
Right.
doesn't matter for us. What matters is only W transpose X. So this point has the same W transpose X as this point.
Okay. Okay.
I mean, here, of course, assuming that this is the W vector, right? Because here the points are perfectly, like this y-axis is the division line. Of course, otherwise it would have been tilted like this. So then points here and here would make the same, would have the same W transpose X like that.
The data point with the least error gives the gamma, right?
Least error.
Because if the error is least, no, it will be closest to the classifier.
See, error is based on both Y and W transpose X, right? So
Yeah.
we cannot say that for any particular given W, we are only looking at W transpose X. So Y is not in the picture.
Sir, in this one, when you said about the gamma, can you just show two examples? Like I just want to see.
Sure.
Any 2 points, any one example, any 2 points.
Sure. I think if I draw it out, it will be easier, right? Because then
that would be better, yes.
So let me say that this is the W.
Correct.
Okay, and let us say that obviously if this is the W, then the orange points are the positive points.
Right.
Okay, and let me take some green points. These are the negative points. Now, the W transpose X is equal to 0 line will be something like this.
Correct.
Okay, and actually let me take a point here also. Okay, here. Now, if you look at this particular line.
Correct.
Okay, all the points that lie on this particular line have the same W transpose X value. All the xi's that lie on this line have the same value for W transpose Xi. Okay, because what is W transpose Xi? It's basically a projection of Xi on W, right? The scalar projection rather. So,
Correct.
Which means that if I project this point on W, still the length along W is only this much. And if I project this point along W, still the length along W is only this much, right? So, for example, let us take this particular point here. As you can see, it is very far from the origin naturally, right? So it is this much distance away from the origin. On the other hand, this point actually has a much smaller distance from the origin, right? But this second point has a bigger value of W transpose X compared to this point for this given W.
Okay, we got it. Because the projection will be that length only, right? Okay.
Exactly.
Fine. I was visualizing it some other way. Okay, fine. Got it.
Sure, no worries. Okay. So we'll move on to the next question. Okay. Initializing at 0 is compulsory in order to implement perceptron. That is false. W0 is equal to 0 is just a convention that we are making to standardize something, right? You can even take this to be a vector of random integers or random real numbers, okay? Or as we have seen in one previous question, we can initialize it to be the vector 1 comma 1, or in general the vector 1 belonging to R D, right? So we can initialize it to be whatever we want. Then irrespective of the choice of initialization, perceptron will converge to a unique W. That is not true. That is not true. Depending on our choice of initialization, it can converge to different W's also. And logistic regression assumes linear decision boundary. That is true. Yes, it does have a linear decision boundary. And there is no possibility to make any adjustments and apply perceptron on a data set which is linearly separable with gamma margin, but by a hyperplane which does not pass through the origin. There is no possibility. This is false. So I can actually come up with. So yesterday we were in the TA session, we were actually discussing like AND gates, XOR gates, and all that. So you can refer to that video also to understand how you can introduce a bias term to so to ensure that the linear separation boundary does not actually pass through the origin, right? So if you have a data set like this, so we can introduce a bias term. Instead of W transpose X, we can have W transpose X plus B. Okay, so we can classify uh, the data points like this also. This is also acceptable. So we can modify, I mean, this is of course not the perceptron that we have seen in the lectures, but it doesn't mean that it cannot be modified to come up with some algorithm like this. In fact, one of the easiest ways you can modify this is, so you have a data set which is D cross N, right? So which is just the columns where the data points are stacked along the columns, which also means that this is feature 1 and so on until feature D. There are D rows and these are the features. Okay, so what I can do is I can add one dummy feature for all the data points, which is just all ones. So instead of a D cross N matrix, this will be a D plus 1 cross N matrix. Okay, in that case, whatever weight I learn here, so the weight vector also, it will correspondingly be a D plus 1 dimensional vector. And this D plus 1th dimension, that is this last row, right? The weight that I learned for that row will be nothing but the bias of this matrix, which means if that is if this weight vector, say it's a weight vector in this W D plus 1, let me say that D plus 1 is equal to 3, which means W D plus 1 is W3, okay? Which means what I can do is I can just take the first two terms of that vector, okay? W1 and W2, which is the first two elements of this vector, and I can keep that as the W. And then this the third element, I can call it B. Okay, so if I plot this W in 2 dimensions and then I use this intercept term, that's how we get this kind of W, which actually does not pass through origin. So this is something that you can do for perceptron. I've discussed this in a little bit more detail in the TA session, so you can refer that also. Okay. So actually only the third option is correct. All the other options are incorrect. Yeah, so they have just said we can use W transpose X plus B. Okay, now consider a linearly separable binary classification dataset with 500 data points and 50 features. So assume that there exists a W such that norm of W is 1. And if nothing is specified about the norm, it's L2 norm, not in squared terms. Okay, and that is root of x2 minus x1 the whole square plus y2 minus y1 the whole square. Okay, Euclidean norm. So now assume that there exists a W such that norm of W is 1 and yi into W transpose xi is greater than or equal to 0.25 for all I. Assume that x2, that is okay, L2 norm of x is less than or equal to 1 for all I. Okay, so what does this actually mean? So what are these two information that have been given to us?
Gamma and radius.
Exactly. So this first point is the gamma that has been given. Okay, and they are saying that gamma is greater than. I mean, every point has makes a dot product which is greater than or equal to 0.25, which means gamma is equal to 0.25. And secondly, they have said that every point has at least this much norm. Norm is nothing but the distance from the origin, right? So this is basically your R. So R is equal to 1, right? So now, what is the maximum number of mistakes that perceptron can make on this given data set? So L is, the upper bound is for L is given by R square divided by gamma square. So this is just 1 divided by 0.25, right? 1 divided by 0.25 the whole square, which is nothing but 4 square is 16. Okay, so 16 is the maximum number of mistakes that perceptron can make on this data set. Right.
Sir,
Yes.
W transpose, can you just go above once?
Sure.
Xi is W transpose, sorry, gamma is W transpose Xi, right?
Yeah, so that's what we've taken, right? So W transpose Xi. So you're asking why we are scaling by Yi, is that right?
Okay, Yi will be 1 or 0, right? Actually.
One. So actually for perceptron, by convention, we take it to be 1 or -1 actually, because that will help us. I mean, just mathematically that helps, because in simple words, if I have this is basically saying, this linear separability assumption is just saying that let me say that I have some points here and I have some points here. So I'm saying that all the positive points are so I mean, so this is the W transpose X is equal to 0 line. Okay, I'm not drawing W for just so that I don't clutter it up, but W is here. Okay, and all the positive points are at least at plus gamma. So which means that W transpose X is greater than or equal to gamma for all I.
Correct.
Okay? And similarly, this is basically saying W
Minus.
transpose Xi is less than equal to gamma for all I.
Minus
This is
gamma,
equal
right?
to minus gamma. Sorry. Yeah. Less than or equal to minus gamma for all I. What I can
Correct.
do is, one thing is for sure that if it is on this side, right? If it is on this side, then Yi is 1, right? Because that's the assumption of linear separability. And if Y is on this side, I can assume it's -1. So simply, I can combine these two conditions into a single condition and say that W transpose Xi times Yi should be greater than or equal to plus gamma. So I can eliminate these two conditions and combine it into a single condition.
Okay, understood.
Okay.
Definitely, it will be positive for Y equal to 1 only.
Yes. So I mean, all the positive points have the label +1, and all the and they will always fall on the side of the decision boundary where it makes a positive dot product with W, with a true W. Okay, so we were here. I think we have completed this question, right? Yeah, we have completed this. So we are here. Consider a data set. X1 is 1, 1, X2 is 1, -1, X3 is 1, -1, -1, X4 is -1, 1. Right? With corresponding class labels, Y1 is -1, Y2 is +1, Y3 is +1, Y4 is -1. So we were given 4 points. Assume that you are using perceptron to find a weight vector W with no bias. Okay, so they've clearly stated that it's no bias. Even if it was not given, we would assume that that is no bias unless explicitly given. Okay, but if they are asking you to find so for example, if they give 4 points like this and they ask you, is it linearly separable? So let us say that these two are I mean, out of the 4 points, these two are plus labeled and these two are minus labeled. Okay, so here, if they're asking you if it is linearly separable, so here you should not say that, no, I won't use the bias term, right? So here you can, even if the question doesn't specify, you can use the bias term to say that there is some linear separability. Bias term basically means weight vector doesn't pass through origin. Okay, for more questions like this, you can see yesterday's TA session, there are a lot of questions like this in the practice assignment actually. So we've discussed these type of questions yesterday. Okay, so
The TA session is uploaded.
TA session actually I'm not yet uploaded on Discourse, but you can access it through calendar. So the link in a few within few hours after the session is done, it automatically, I mean the same link you used to join the session, right? There you will be able to see the
I think
recording.
someone said it was asking for request access.
Okay, I guess if it's not working, then you can tag me on Discourse. So the thing is, actually, for the TA sessions, from what I have observed, the recording gets generated within few hours, but immediately for the next few hours, or even for the next half a day, sometimes the recording is not accessible to anyone. Which means you can see that the video is there, but if you click on it, it will say access denied. But I've actually personally gone to Mayur sir's office and seen that it is only enabled. I mean, there is no restriction for the access. Mostly it is anyone who uses the IITM email should be able to access. So that is the permissions that is set for the video. But for some reason, for the first few hours, it is not accessible. If it is still not accessible, please make a post on Discourse for it, and I'll request my user to look into it. Okay, so yeah, so let's consider this data set. And let's say, okay, we are using positron to find a weight vector W, and we decide to cycle through the points in this order. So normally, if nothing is given, we'll use the same order, x1, x2, x3, x4. But here they've given an order, x4, x3, x2, x1, until a linear separator is found. The question is asking, what is the number of mistakes? And secondly, what is the squared length of the weight vector corresponding to the final linear separator your algorithm outputs? Okay, so this looks like a detailed question. Okay, so let's start. Have they given anything about W initialization? Nothing, right? So we just start with assuming that W0 is equal to 0, 0. Okay, because they've not given anything about what is the initial W. Right, so now we have to go in this order. So what I'll do is I'll take W0 transpose with X4, right, and see what is the sign of that. So W0 0, 0. So dotted with anything that is going to give me 0 only. Right, so W0 transpose all the points is going to give me 0. And the sign function is basically if it is greater than or equal to 0, then I'll assign the class +1. Otherwise, I'll give the class -1. So which means this point is going to classify every point as +1 class only, right? So it correctly classifies the first point because that is it makes a mistake on the very first point itself because we predict +1 class, whereas the true label, so this is y hat, by the way, this is y hat, whereas the true label for y is actually -1 because this is -1, right? So in the very first iteration, positron has made a mistake. Okay, so which means that we have to update W now. We will get W1.
Sir,
Yes.
Shouldn't we take Y4 as the label for X4?
Sorry, my bad. I was saying that we have to take Y4, but by mistake I took Y1, as a habit. Okay, so yeah, so this is, I mean, luckily for us, this is also with the label -1. But yeah, you're correct that we have to take X4, Y4. Okay, and yeah, this also makes the label +1, whereas this is -1. So using this, we now have to update W1 is equal to W0 plus X4 times Y4, right? So this is how we have to update it because this is the point on which we made a mistake. So W0 plus X4 times Y4. And what is X4? X4 is, so actually let's look at Y4 first. Y4 is -1, which means I can replace this, right? So I can just write this as, I can write this, yeah, I can write this as minus. W0 minus X4. W0 was 0, 0. Minus X4, which is minus of -1, 1, So it's just 1 minus 1. Right? W1 is 1 comma minus 1. Now again I have to start at this point because we are cycling through the points in this order. So let's see for this particular point. W1 transpose with x4 is going to give me 1 comma minus 1 times, sorry, dot with minus 1 comma 1. So this is going to give me minus 2, right? Minus 2, which is less than 0. So I will give it the class minus 1. And the true class is also minus 1, so we are fine. We are fine. So next I'll go to x3. So W1 transpose with x3 is giving me 1 comma minus 1 dot x3 is minus 1 comma minus 1. This is 0, right? So this is 0. So I'm assigning it the label plus 1, right? Whereas, okay, so here the label is plus 1 only. So this is also correct. And let's go to x2 now. So W1 transpose x2 is equal to W1 transpose x2 is 1 comma minus 1 dotted with 1 comma minus 1. So this is 2. 2 is greater than 0. So this is the label plus 1, and y2 also has the label plus 1. So we are good so far. So hopefully if it classifies the last one also correctly, W1 transpose x1 also correctly, we are done. Okay, 1 comma minus 1 dotted with 1 comma 1, which is 0, right? So 0, so we will call it plus 1. What's the actual class? The actual
Minus
class
1.
is minus 1. We have to do one more algorithm, so one more iteration. Okay. Okay, just to confirm that I've not made a mistake. It seems to be going on for multiple iterations. Okay, anyway, we have to do one more iteration only. So here it made a mistake on x1, right? So we'll update it with x1. So we'll get W2 is equal to W1 plus x1 times y1, right? And y1 is what? Y1 is minus 1. So this is minus x1. Okay. W1 was 1 comma minus 1 minus x1. What is x1? 1 comma 1. So 1 minus 1 is 0, minus 1 is minus 2, right? So please correct me if I'm making a mistake somewhere. I think so far it's correct. Right, so this is W2. Now let's cycle through all the points again. Okay, so W2 transpose with x1 is 0.
This time let's start from x1 or x4 again.
Sorry. Thanks for pointing that out. W2 transpose x4 is this, right? So I think, yeah, we can reuse the same values here. So this is minus 1 comma 1 is, so I just need to look at the second coordinate now. This is minus 2, which is less than 0. So this is y hat and this is true label y. Okay, so I'll just plot a simple table like this. So y hat is minus 1 and the true label is minus 1. Okay, now W2 transpose x3 is equal to 0 comma minus 2 dotted with minus 1 comma minus 1. Okay, so that is minus, so this is plus 2. So this is plus 1 and the true label is also plus 1. Right, so yeah, true label is also plus 1. Now W2 transpose x2 is equal to 0 comma minus 2 dotted with 1 comma minus 1 is plus 2 again. So this is plus 1 and this is also plus 1, right? Now the final one Hopefully, if we get this, we don't have to do this one more time. Okay, so this is x1 is equal to 0 comma minus 2 times what is this, 1 comma 1, right? So that is equal to minus 2, thankfully. Okay, so which means this is minus 1 and this is also minus 1. So all the 4 points are correctly classified. Okay, so it was a, it was a tedious task computing this through 3 iterations, but it's worthwhile because basically this is, now you get a feel for how actually perceptron works, right? So every iteration, this is what happens. You cycle through the points in, first you predetermine an order. You can't take a random order in every iteration, but at first, in the first iteration, you have to specify some order, and every iteration you have to follow the same order, and you see at which point it makes a mistake, and you take that point. Using that point, you update W and get the next W, okay, for the next iteration, and then in the next iteration again cycle through all the points until you make a mistake. And if you make a mistake, then don't go to the subsequent points. Just stop there, update the W, and start from first again. Okay. And finally, if you get a particular value of W for which it doesn't make a mistake on all the training points, then you're good. Okay. Then it means that perceptron has converged. So what have they actually asked in this question? The first is, what is the number of mistakes? So let's see. So this is actually W2, right? So we had
Srinivas, just one maybe very basic stupid question. This W transpose X, both are column vector, right? How we are doing multiplication, is it, or
it's a dot product?
Oh, it's a dot product. Okay.
Yeah, because W is also belonging to RD. In this case is R2, and X is also belonging to R2. In fact, we initialize W as 0, 0 based on X only. Okay, so because X is two-dimensional, all the X's are in R2, therefore we initialize the W also to be in R2. Okay, and then we are taking a dot product of W with each of the X. Of course, in a single dimension, a dot product is nothing but regular multiplication.
Okay.
All right. So now we were looking at how many mistakes perceptron has made. Okay, so in W0 we had a mistake, and therefore we moved on to W1. Right. So this is one mistake. Then W1 had a mistake, therefore we went to W2. So that is another mistake. Do we have a W3? I think we don't have a W3. So only 2 mistakes, right? So we made one, let's see, we made one mistake, which is the exact mistake. So W0, for the first point itself, it made a mistake, correct?
W0 consider, because that's an initialization. Right?
Correct, but only once it makes a mistake, you update it, right? So that mistake is also counted.
Okay. So basically we have to, see W0 transpose X for all the points.
Yes, and what we had is, because unless it makes a mistake, then you will never move from W0 to W1. So in this case, it made a mistake on X4. X4 was the first point we saw. So it made a mistake here. So that is the first mistake. Then we updated it to W1. W1 actually classified all these 3 points correctly, but it made a mistake here. So that is the second mistake. And then after that, we got W2. W2 classified all 3 correctly, which means that the number of mistakes that perceptron made here is 2. Second one is, what is the squared length of the weight vector corresponding to the final linear separator? So this W2 is our final separator, right? So it is 0, minus 2. So naturally the length of this is nothing but, yes. But they're asking for squared length. So this is, they're asking for squared length. So this is actually 4.
4.
Right, so the question is asked for what is the squared length? So it is 4. Okay, so let's check. Yeah, it is 4, and this is 2. Okay, so we're done with this question as well. I think every page is becoming smaller and smaller.
Also, number of mistakes is for all iterations.
Sorry, number of mistakes is for what?
For all iterations. So,
Yes. A reason being, if you make a particular mistake on, like for example, let's take this question itself, right? So we have made a mistake in for W0, it made a mistake with respect to the first point itself, correct? I mean, sorry, which is x4. The first point was x4, right? So it made a mistake with respect to x4 itself. And after that, we did not even check W0 with x3, x2, and x1. Correct? We immediately stopped that iteration. We updated W to W1, and then again we started from x4 only. We didn't continue from x3. So which means that number of mistakes is actually exactly same as number of iterations. In every iteration, you make only one mistake. That is a characteristic of perceptron. Okay. Alright, so consider a logistic regression model that has been trained for a binary classification problem on a dataset in R2. And the weight vector is given as half comma 2/3, right? So given a test data point as input to the model, it returns 1 as the predicted label if the probability output by the model is greater than 0.60, okay, and 0 otherwise. So normally we would keep the probability threshold as 0.5, right? Whereas here they kept the probability threshold as 0.6, which means if 1 divided by 1 plus e power minus of w transpose x, if this is greater than 0.6, then it gets the label +1. Otherwise, it gets the label 0. Okay. That is y is equal to 1. Sorry. Y is equal to 1 if this condition satisfies, and y is equal to 0 otherwise. So this is our classification condition. So what is the predicted label for the test data point 1, 0? So let's predict it. Of course, they have given the sigmoid function in case we forgot, but we didn't forget, right? So now we have the probability. Since they use the notation of sigma, we'll also use that sigma of W transpose X, right? So first we need to compute W transpose X for that. This is W1 half comma 1/3, sorry 2/3 transpose with X. What is X? X is 1, 0. So this is just 0.5, right? So half into 1.5, this is 0. So this is just 0.5. So now sigma of 0.5 is nothing but
Srinivas, sorry, I always get confused. We should not bother here, right? Whether it is transpose or state calculation. It will ultimately give the same value.
yes, actually, in our lectures, if you observe, we never use the dot product directly. So we never say that, if you use the vector notation. So for example, if we say that this is the vector x and this is the vector y, then we would just define dot product like this. So in most math textbooks, you would have seen it dot product defined like this, correct? But for this course, we are omitting this arrow notation. So we are using vectors also. We are representing vectors also as just alphabets without any, further arrow symbol to indicate that they are vectors. So the dot product notation is now no longer x dot y because that could be confused for multiplication. So the dot product notation is given as x transpose y. So with this notation, you cannot make a mistake, right? So because this just becomes matrix multiplication, but it's just a fancy way to say dot product. It's just another way. I mean, I won't say fancy way, but it's just another way of writing the dot product notation. So when I say x transpose y and x and y are both vectors, so please understand it to be x dot product with y.
Okay, so we can just put the values like this and do the dot multiplication. No need to take transpose of W.
Yes, assuming both are vectors.
Okay.
Okay, so obviously this does not hold when one of them is a matrix, right? But because obviously the matrix x multiplication with y is not the same as x transpose multiplication with y. These two are not the same. But for vectors, yes, x transpose, You need not take the transpose or something. It just turns out to be the same. So if I do take the transpose, what will happen is, so both are column vectors. So this will become half, comma 2/3, and then this will be 1 0. So at this point, it is just a multiplication of two matrices. So this transpose notation just converts this vector notation to matrix notation, actually. So this is different notations of representing the same thing. So this will be a
ultimately,
1 cross 2 matrix multiplied by a 2 cross 1 matrix. So the result will be a 1 cross 1 matrix, which is just a single number belonging to R.
so ultimately, even though if we say W transpose X or we say WX, it is ultimately same. We mean to say same, but just to notify it is a dot product, we are using W transpose X.
Correct. So this notation, we just mean to say W dot with X. That's what it means.
Yeah. Okay, fine.
So yeah, good that you got that clarified, because I mean, this is because we use this notation very often, and it's
Yeah,
important to
looks
get.
like very basic things are not clarified means we cannot build up. I get lot of confusion.
Yes, so I mean, now hopefully that should be cleared up, right?
Yeah, fine. Very
Because
clear.
from the very first week, we have been continuously using this notation only. So now, if you go back and revisit those topics, it should be more clear now.
Yes.
All right. So coming back, so this is W transpose X here is 0.5. Right, it's 0.5. So 1 divided by 1 plus e power minus 0.5. Right, so this is 1 divided by 1 plus 1 by e power 0.5. So can someone tell me what this number is?
0.622 total value.
E
The
value is
1 divided by
2.54,
or
right?
just
Final value.
the final value of this entire expression?
0.62
Okay, 0.62, right? Okay, so
plus 1.
yeah, so it's 0.62, which is greater than 0.6. So we denote it as +1 class. Is anything else asked? So what is the predicted label? It's +1. Yeah, so they're just asking what is the predicted label, that's all. So it is +1. Yes, okay, so it's +1. Okay, so now we have a logistic regression model trained for a binary classification problem with features in R2 and labels in 1, 0. So when we say labels in 1, 0, this means either label is 1 or it is 0. So if I use this kind of parenthesis, it means, or if I use square brackets, it means that it is a continuous interval, actually. So this is an open interval where 0 and 1 are not included in the interval. This is a closed interval where 0 and 1 are included. But this means all real numbers between these 2 points. Whereas if I use curly braces, then that means that only those 2 numbers are there. This is a set notation, right? So only the labels are either 0 or it can be 1. Only these 2 possibilities. So now the probability that the test point 1, 3 belongs to class 1 is equal to 0.75. What is the probability of the test point -1, -3 belonging to class 0? Okay, so one thing that we can say, so there is some W, okay, so there is some, let us say that there is some W, and this W is equal to W1, W2, okay, this is the W vector. Now, if I take this W transpose X, okay, then what I get is W1, W2. Okay, so I mean, we're just trying out stuff for this question. I mean, we just to see what is the approach. Even I don't know if this is going to be the correct approach or not. But yeah, so we have 1, 3, and we get W1 plus 3 W2. Okay, and we plug in this value W1 plus 3 W2 inside the sigmoid function, and we got that thing 0.75 is the probability. Is equal to 0.75. Okay, now if this is the other point, okay, the other point, this is x1, and W transpose x2 is now W1, W2 I can take the minus outside. So this is minus point. So this should actually be W1 plus 3W2, right? And sorry, minus of W1 plus 3W2. Okay, so what I can do for this point is, okay, so one you know what, one fact that we can use is this point is exactly as far away on the negative direction as the point 1 comma 3 is from W in the positive direction. So if we have this particular data set, right? If we have this particular data set, this is the W, let's say, and we have the positive points here, right? And we have some negative points here. So I can draw this decision boundary, and let's say this is the set of all points for which, or you know what, let me take this. This is the set of all points for which W transpose X is equal to some theta. Okay, and naturally this will be the set of all points for which W transpose X will be equal to minus theta, right? And so if I take this point, if I take a point that lies on this boundary, it will have some probability of belonging to the positive class. So which means that any point which is on this side, on the exact same distance away but in the negative direction, should have the exact same probability but of belonging to the other class, of the negative class, correct? So which means this point, if it has a 0.75 chance of belonging to class plus 1, then this point will have a 0.75 chance of belonging to the class minus 1 or 0, as the case may be, right? So of belonging to the negative class, so class 0. So in this case, the other point has a 0.75 chance, right, of belonging to the negative class, because it makes the exact same dot product but the negative of it. Okay, so if this makes I mean W1 plus 3W2 is equal to some theta dot product with it, then this makes minus of W1 plus 3 times W2. So it makes a minus theta dot product with that weight vector, right? So because of that, we can conclude that the probability of the point belonging to class 0 will be 0.75. If they had asked for that point, what is the probability of class 1? That is just 1 minus 0.75, which is 0.25. Okay. Right. You can also solve this mathematically, I think. So I haven't properly formulated this in my head yet, but so if you have probability of y is equal to 1 given x1, it was 1 divided by 1 plus e power minus of w transpose x, so e power minus theta, right? So which is equal to, we said that this is 0.75. So probability of y is equal to 1 given x2 is going to be 1 divided by 1 plus e power minus of minus theta, which is e power theta, right? And can we say that these two should add up to 1? So this is, if I expand this, I'm just thinking out loud, okay? So this may not lead anywhere, but I think it will.
Yeah, if we add these, it will become 1.
Yeah, they should become 1, right? Ideally. So I'll just take so this is e power theta plus 1 divided by e power theta. So this will go here, right? So this will go to the numerator. So that is nothing but e power theta divided by e power theta plus 1. Correct? And this is 1 divided by e power theta plus 1. So which means that these two have to add up to 1. Correct? So which means that this is equal to 0.25. Can I say that? So probability that y is equal to 1 for the second point will be 0.25, which means the probability of y is equal to 0 for the second point is going to be 0.75. So we can also prove this mathematically. Of course, it's easier to see the geometric intuition behind this, but you can also prove this purely mathematically. Okay. All right. So do we have any more questions? Yeah, I think we have come to the last question here. All right. So logistic regression model assigns probabilities to classes based on a linear decision boundary, right? So the test point 1, 3 has a probability of 0.75 of belonging to class 1, which implies a probability of class 0 for 1, 3 is 0.25, right? Because it has to add up to 1. So this point, it has 0.75 chance of belonging to class plus 1, sorry, plus 1, and 0.25 chance of belonging to the class 0, right? Class 0. Now, assuming symmetry in the logistic regression model, the probability is flipped for the, oh, okay, so this is actually just the answer to that question. This was not a separate question. So this was just the answer to that question. And they have actually used the same method that we used initially. So because this model is symmetric, so this point is makes the same W transpose X plus W transpose X with this W as this point makes with minus W, right? So in the other direction. So that's the logic that they have used actually for this solution. So actually, yeah, that's it. We are done with all the questions, and that's about it. So if there are any doubts, you can ask. Otherwise, we can wind up the session.
Is it where is this question, sir?
So these questions are actually Mayur sir shared this PDF to me, so I'll probably add it in the calendar link, or I'll ask him where he generally posts it, and wherever it is usually posted, it will be posted there.
Sir, on the calendar and also on the dashboard.
On the dashboard, okay. On the dashboard, Mayur sir will post that. Probably, I think even for calendar, I don't think I can add it there. I'll request him to add it. Okay, because I don't have access to update the calendar. But yeah.
Okay. The class is over, right?
Yes. All right, so that's about it. Let's wind up the session. Okay. Thank you everyone for joining.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.